Hello again. So, in this, what will hopefully be short uh, lecture, we're going to talk about expected value. And what is that? Well, let's talk about a question one might have about uh, an experiment with a random outcome. So, suppose um, we have some experiment. We have an experiment um, whose outcome is described by, let's say, the random variable x. Okay, then the question one might have, so the question is, if we repeat this experiment many times, so if we run this experiment many times, what is the average outcome? Now, in general, you will never know exactly what, so if I run the experiment 10 times, there's no way I can predict what the average of those 10 will be, because well, it could be many things, but what we do expect is that if we run some experiment many, many times, the average will generally approach some value, right? If I roll a die many times, so an example where we don't even need to really compute anything to know this. So if we roll a die many times, well, we expect to have roughly the same number of ones as twos, as threes, as fours, as fives, as sixes, etc. So we would expect to have um, roughly same number of ones, twos, threes, sixes, etc. Because they're each equally likely, so if we do this lots and lots of times, we'll have roughly the same number of all of them. And thus, on average, the value of the die, so on average, the roll will be will be well, the average of 1 through 6. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. And that equals 3.5. So on average, you roll a 3.5 every time you roll a die. But it's not always as easy to compute as that. So in general, how might we compute this average value? So how to compute this? Or actually, I should say first, so we call this average value the expected value so that's the technical term, is the expected value of x. X is the random variable, and we call the average behavior the expected value, and we denote it E, capital E, and then square brackets x, right? And whatever expected, so if we wanted to take the expected value of some random variable y, it would be E of y. So how do we compute this in general? Well, one way is to simply take the average of a perfectly representative sample. One way would be to take the average, or mean, same thing, of a perfectly representative sample. And that's feasible to do sometimes, but in general, it's a very cumbersome approach. So we're going to develop a better way of computing it. This is the simplest way of computing it, and we'll see an example. And by processing the example, we will come up with a more general formula. So our example is, let's say you're playing a game where you roll a die. You roll a die, and if you roll a 6, you win 10 bucks. If you roll a 6, you win $10. And let's say otherwise you lose $3. You lose $3. All right, so if you roll anything other than a 6, you lose $3. And if you roll a 6, you win 10 bucks. All right, so this is some kind of betting thing, right? And the idea is, so the question you would want to ask is, if we played this game lots of times, on average, how many dollars would you earn or lose per time that you played? So on average, how many dollars do you win / lose every time you play? And so to answer this question, we describe the outcome with a random variable x and compute its expected value. So let x equal so the dollars that you win or lose. So like your change in the amount of money you win or lose. And then we want the expected value of x. All right, so to compute the expected value, first we need a probability distribution. So there's only two possible values for x, right? You either win 10 or you lose 3. So it's a pretty simple probability distribution. So k probability x equals k. It's either -3 or it's 10. Right? And so -3 happens if you roll a 1, 2, 3, 4, 5. So that has probability of 5 out of 6. And then +10 happens if you get a 1 out of 6. Right. So this describes the experiment. And to get a perfectly representative sample, right, we need 5 -3s and 1 10. So a perfectly representative sample looks like so you have 5 -3s and then 1 10. So the frequency of 3s in this sample is 5 out of 6, and the frequency of 10 in this sample is 1 out of 6. So the average value, so the average of this sample is, well, -3, -3, -3, -3, -3, 1, 2, 3, 4, 5, so +10 divided by 6. And that equals, well, the 3's add up to -15, plus 10 is -5. So this equals -5 out of 6. So this says the expected value of x equals -5, 6. So we expect to lose, well, that comes, if you compute it, that comes out to 83 cents every time we play. Well, that kind of sucks. So in other words, don't play this game. Obviously, you could get lucky, win 10 bucks on your first go, and never play again, in which case you would have beaten the odds, as it were. But in general, it's not a game you should play. Okay, so let's look at how we did that and get a formula that we can use to compute this more generally. So we computed, we had -3, -3, -3, -3, -3, plus 10, right? If we look at that another way, so if I combine the multiple 3's together, right, I have -3 5 plus 10 times 1, right, divided by 6, and that is -3 times 5 out of 6 plus 10 times 1 out of 6. All right, so just rearrange this slightly, but what do we notice here? 5 out of 6 and 1 out of 6 are precisely the probabilities of getting -3 and the probability of getting 10, right? So this equals -3 times the probability that x equals -3 plus 10 times the probability that x equals 10. Right? And this is really how we want to compute expected value in general. So if we have a probability distribution for x that looks like all right, so I'm going to make a general distribution, so we're not going to be specific. So we'll have k, probability that x equals k, and I don't want to commit to any specific value, so I'll just call it k1, k2, k3, dot 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 up to kn, right? It could have n different values. I don't really care what they are, or I'm just trying to be as general as possible, right? And so this will be probability 1, probability 2, probability 3, probability n. Then the expected value of x equals k1 times p1 plus k2 times p2 plus k3 times p3 plus dot 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 plus all the way up to kn times pn. So we simply add each outcome, each possible value that the random variable can have, times the probability that it occurs. And we just sum that up, and that's all. That's how we compute expected value. Now I want to make one note, and this is something that we should remember. So note, if x is a binomial random variable, if x is binomial, alright, back to work. Alright, so if x is binomial, let's go full screen. Is binomial with, so we have n and p. Those are the number of trials. So this is number of trials. This is probability of success. And the expected value, which you might expect, no pun intended, is just equal to the number of trials times the probability of success. So this is, on average, how many successes you will have per trial is simply, or how many successes you will have after n trials is simply the number of trials times the probability of success. The other thing, so that's one thing that we should remember. Another thing is that on average, the average value of sort of x plus y, if we have a random variable that's the combination of two other random variables, right? The average value of the sum is simply the sum of the average value. So this equals e of x plus e of y. All right. So that's all the theoretical stuff. Let's get into doing this, doing the examples. Really struggling. All right. Here we go. So what is the expected value for the random variable x, which has the following probability distribution? All right, this is completely straightforward. We're just going to follow the formula. So the expected value of x equals -1 times the probability of -1, which is 0.1, plus 0 times the probability of 0, which is 0.2, plus 1 times the probability of 1, which is 0.3, plus 2 times the probability of 2, which is 0.4. So this comes out to be minus 0.1. We don't need to take into account 0, that disappears, plus 0.3, plus 0.8, and that equals 1. So on average, x, the outcome of this random experiment, right, is just 1. So if you do it 100 times, you'd expect that your the sum of all of them should be roughly 100. Anyway. So let's look at the next one. So 2 dice are rolled, and the larger value is recorded. What is the probability distribution for this experiment, and what is the expected value? So on average, if we roll 2 die, what should we expect the larger value to be? is kind of subtle, but let me walk you through the sort of the first half, and then I'll let you do the second half of this problem on your own. So the first step, and this is often the first step for such problems, is find the probability distribution. So let's compute the distribution. So we know that the maximum value can be anything between 1 and 6. So if k, probability of x equals k, 1, 2, 3, 4, 5, 6. Alright, so let's start with 1. If the maximum value of both dice is 1, that means they're both 1. So 1, 1 is the only way you can have the maximum value be 1. So only one way. Only way out of the 36 possible ways, so this is 1 out of 36. If the maximum value is 2, well, there's 2 ways, right? You could have 2, or there's actually 3 ways. 2, 1, 1, 2, and of course 2, 2. So there's 3 ways. So we have 3 out of 36. If we have 3, right, let's see how many ways. Well, they could both be 3. Or we could have 3 and 2, and that's also 2 and 3. Or we could have 3 and 1, and that's also 1 and 3. And this is all of them. So this is 5. So we have 5 out of 36. Alright, so maybe I will stop here, but what I want you guys to do is finish the rest of this problem. So what you need to do is compute the probability distribution, and then do the same procedure we just did for the problem above. We compute the expected value by saying 1 times 1 over 36, plus 2 times 3 over 36, plus 3 times 5 over 36, etc. And then you'll compute the second half of the probability distribution so you can complete that. All right. Now, but let me let's walk through problem 8 first. You pay $1 to play the following game. You draw 2 coins from a bag containing, this should say 2 $1 coins and 6 worthless coins. You get to keep any $1 coins you draw. Is this a smart game to play to make money? Alright, so I want to figure out what, on average, how much money we make from this game. So we need to compute, first step is compute the probability distribution. So k, and then the probability that x equals k. Alright, it's implied that x is the random variable describing the amount of money you make playing this game. So let's say we have only 3 possibilities. Either you lose $1, right, because you have to pay to play. So if you draw only worthless coins, then you just lost $1. You could break even, right? If you draw exactly $1 coin, then you just broke even, or you could make $1. And so we want to figure out what the average outcome is. If maybe on average you'll make money, then you should just play the game a lot of times and you could make some money. Or maybe you'll lose money every time. Alright, so what is the probability of drawing only worthless coins? Well, you're drawing a pair of coins. There's 6 worthless and 8 total. So there's 6 choose 2, right? Pairs of worthless coins you could draw out of 8 choose 2 total pairs of coins. Right. So that one's slightly simple. If you want to break even, you need to draw 1 coin, $1 coin, and 5 worthless coins. Or sorry, and one $1 coin and 1 worthless coin. Right, you're drawing a pair. So the number of pairs of a $1 coin and a worthless coin, well, you select 1 $1 coin. There's 2 choose 1 ways to do that. Then we select our worthless coin, and there is 6 choose 1 ways to do that. And then of course there's 8 choose 2 total ways to choose pairs of coins. Alright, so that's the probability of breaking even. And then the probability of gaining a dollar means that we both times choose a dollar coin. So there's 2 choose 2 ways of choosing $2 coins divided by 8 choose 2 total ways to choose pairs. Alright, so this equals 15 out of 28. And this equals 12 out of 28. And this equals 1 out of 28. Okay. So the expected value here, so e of x equals minus 15 out of 28, minus 1, I just didn't write the 1, plus 0 times 12 out of 28, plus 1 times 1 out of 28. So this equals minus 14 out of 28 equals minus 1/2. This says on average you lose 50 cents every time you play. So on average you lose half a dollar every time you play. Alright, so this is probably not a smart game to play to make money. So the answer, the literal answer to the literal question is no. Don't play. Unless, you just like gambling, and then go ahead. Anyway, that's all for now. I'll see you in the next video.